This video is introducing the hyperbolic functions, but first we actually need to talk about what a hyperbola actually is, because you've never actually come across it before. It used to be taught quite a lot in the old A level, but it's not actually taught at all really now under the new specification, apart from in the use of hyperbolic functions. This is the hyperbola on the right hand side over here. That's what a hyperbola looks like, and it's defined in a similar way to a circle. So just very quickly, the recap of a circle is obviously all of the points that have the same distance away from the origin. Every point on this circle is the same distance away from the origin, away from the centre. And if we're talking about the unit circle on the origin, then the equation of this is x squared plus y squared equals 1. Now a hyperbola doesn't have one centre. In fact, it has 2 points that are called the foci. It has 2 focus points. And the hyperbola is all of the points where the difference in the distance between the foci is a constant. Now that sounds quite clunky, but if I just show you what I mean, it'll hopefully make sense. All of those points I've just marked on, if I were to measure the distance between this point and this point, and if I was to measure the difference in those distances, it would be the same as if I was to measure the difference in distance between this point and this point, or this point and this point, or this point and this point. Basically, it is any point on the hyperbola, the difference in the distances from the foci is constant. So that's how the hyperbola is defined. And if we're talking about the unit hyperbola, then it has the equation x squared minus y squared is 1. So that's what a hyperbola looks like and how it's defined. Now, the trigonometric functions, you've obviously been used to dealing with sine and cos since, before GCSE really. You would have encountered them for the first time, and you were introduced to them via triangles. And you were told that sine is defined as being the opposite divided by the hypotenuse, cos is defined as being the adjacent divided by the hypotenuse, and so on. But then what we saw in year 12 trigonometry is that actually they're more general than that, and then they're not just specific to triangles. They actually can be defined in terms of the unit circle. And we saw that if we were to take any point on a unit circle and measure the angle from the positive x-axis, then we can define the x-coordinate of that point as cos theta. And we can define the y-coordinate of that point as sine theta. So we have these new definitions for cos and sine. Cos is the x-coordinate, sine is the y-coordinate. And that gave us the identity cos squared plus sine squared is 1. Now, we can apply the same logic to the hyperbola. If I pick a point on the hyperbola and measure the angle that it makes with the positive x-axis, then I'm going to define 2 new functions as the x and the y coordinate of that point. I'm going to define the x coordinate as being cos hyperbola, and I'm going to define the y coordinate as sine hyperbola. So cos h theta, sine h theta. Now we don't actually pronounce them like that. We actually pronounce these in a kind of funny way. The first one, function here, is just pronounced as cosh, which kind of makes sense. It looks like cosh. So cosh is the x-coordinate of the unit hyperbola. This, we say sinh. Sinh is how you pronounce that. So sinh is the y-coordinate of the hyperbola. And that's going to give us a new identity, which would be cosh squared theta minus sinh squared theta is 1. So that is how we are defining these two brand new functions, cosh and sinh. They're being defined in exactly the same way that cos and sine were with the trigonometric functions, but they're being defined in terms of the hyperbola, hence why it's cosh and sinh, and not the circle. Now, in the same way that we have other definitions for cos and sine, we can have other definitions for sinh and cosh. So sinh is being defined as e to the power x minus e to the power minus x divided by 2. And I'll show you why these new exponential definitions work in a moment. So these are the exponential forms of sinh and cosh. So just in the same way as we have different definitions for sine and cos, dependent on whether we are talking about the unit circle or whether we're talking about right angle triangles, we can have different definitions for sinh and cosh. And we can also introduce tange. Remember that tan was sine over cos, well tange is sinh over cosh, which I could also write as, if I wanted to write that in exponential form, I could write it as sinh times 1 over cosh. Now sinh, I know, is in terms of exponential form. This is me just taking the formula from above, multiplied by the reciprocal of cosh. So if I do the reciprocal of this, and you can see that the 2's will cancel out, and so I'll get that tange can also be defined as being e to the x minus e to the minus x over e to the x plus e to the minus x. And there is a third way of defining tange that I actually prefer, and it's just about simplifying this expression, because this expression here, it's quite messy with all of those exponentials. But what I can do to make this simpler, if I times everything on the top here by e to the x, and do the same thing on the bottom, then that's good to do, because then on the numerator I've got e to the x times e to the x, so that's going to be e to the 2x. And then, crucially, I'm going to have e to the minus x times e to the x, which will cancel out just to be 1. And then similarly on the bottom, I've got e to the 2x plus 1. And for me, this is a nice, well, slightly nicer version of the exponential form of tange. So we have got sinh is being defined as the y-coordinate of the unit hyperbola, and cosh being defined as the x-coordinate of the unit hyperbola, and how they then give us the equation x squared minus y squared is 1. Let's see now if these new exponential definitions still work with the hyperbola. So I've written all this out. I'm just going to talk you through it. So remember, this is the equation for the unit hyperbola, and I'm saying that x is cosh theta and y is sinh theta. And now I'm just substituting in these exponential forms of cosh and sinh. So here is cosh, here is sinh. So I'm expanding the brackets first of all. So e to the x squared is e to the theta squared is e to the 2 theta. Then I have e to the theta times e to the minus theta, and then I have 2 of those. And then I've got e to the minus theta squared. And all of that is over 2 squared, which is 4. Then I've expanded the same bracket over here. The other thing to note on the next stage is that e to the theta times e to the minus theta will cancel out. And so this middle term will just be 2. And similarly over here, this middle term will be minus 2. Now we have our brackets as simple as they can be, so I'm going to now add, or rather subtract, these 2 fractions away from each other. E to the 2 theta minus e to the 2 theta, they cancel out. The e to the minus 2 theta and the e to the minus 2 theta, they cancel out. And so I just get left with 2 minus minus 2, which is 4, over 4, which is 1. And so we can see then that these exponential forms of cosh and sinh do work with the hyperbola. They are valid definitions for cosh and sinh in terms of exponentials. We can also define the reciprocal, hyperbolic functions. So 1 over sinh, I think it's called cosec, and that's just the reciprocal of sinh. 1 over cosh, I think called sech, again just the reciprocal of cosh. And then I think it's cough. I'm not too sure about those things. We don't use them that often, or at least I've not used them that often. But they're just the reciprocal of the hyperbolic functions in the same sort of way as that we have the cosec, sec and cot inverse reciprocal trig functions. Right, so that's all of the definitions out of the way. Let's look at these functions in a little bit more detail now. So first of all, let's look at an example of substituting into a hyperbolic function. So here I want to substitute ln4 into Tange. Remember that Tange x can be thought of as e to the 2x minus 1 over e to the 2x plus 1. And I'm substituting ln4 in instead of the x. In order to work that out, notice I want the exact value here. So I'm going to take this 2 and move it to be a power on the 4. Take this 2, move it to be a power on the 4. So I'll get e to the ln4 squared minus 1 over e to the ln4 squared plus 1. The e to the ln's cancel out. So I get 4 squared minus 1 and 4 squared plus 1. So this is the exact value of Tange ln4. So that's an example of me substituting in to a hyperbolic function. Now let's have a look at an example where I'm told what the hyperbolic function equals, and I need to figure out what I'm substituting in. So I'm basically solving the equation here. So it says use the definition of sinh to find to 2 decimal places the value of x for which sinh x equals 5. So the definition of sinh is e to the x minus e to the minus x over 2, and I'm told in this question that equals 5. So to solve this equation, I'm going to times through by 2 to simplify this. And then, just in case you can't spot what you need to do here, we can always rewrite this e to the minus x as being 1 over e to the x. That way, hopefully it's clear that you can see that in order to solve this equation, we're going to multiply through by e to the x. So e to the x times e to the x is e to the 2x. And the 10 times e to the x is 10e to the x. Moving everything over to one side now, because hopefully you can see here we've got a hidden quadratic. So I'm going to make a substitution. I'm going to say let t equals e to the x, because then t squared would be e to the 2x. So that's going to give me the equation t squared minus 10t minus 1 equals 0, which then allows me to see, solving that either by using your calculator or completing the square, t is either going to be 5 plus or minus root 26. Now substituting back, e to the power x was my t. So e to the power x equals 5 plus root 26. Notice that I have ignored the negative here, and that was on purpose, because I know that e to the power x is always positive. Remember what the e to the power x graph looks like? It's always positive. Therefore, I know it can't ever actually equal 5 minus root 26, because 5 minus root 26 is negative. All I'm going to do now is take logarithms of both sides. And I could leave my answer like that to be an exact form, but the question wants me to have it as a decimal. So let's type that into your calculator. And we're done. Right, let's now look at the graphs, just to finish this video off. So we're going to look at the graphs of sinh, cosh and tange and see what they each look like. So sinh, first of all, this is the graph of sinh. I'm just going to show you how we know that's the case from the definition. Let's remember that sinh is defined as being e to the x minus e to the minus x over 2. To make my life a little bit easier, I'm going to think of that as being e to the x plus minus e to the minus x over 2. Hopefully it's obvious that this is the same thing as this. The reason why I'm doing it like that is because now I can think of the graph of e to the power x, which is this line, and the graph of minus e to the minus x, which is this line, and then I can just add them together and divide by 2. And hopefully you can see from this diagram that adding those two, the green highlighted and the yellow highlighted lines together, they're going to give me the sinh graph in the middle there. So this is the graph of sinh. Notice it's a one-to-one function. So its domain is unrestricted, its range is unrestricted, and its inverse function that we'll deal with in the next video exists with a one-to-one function. Now let's look at cosh. Again, let's remember that cosh is the same thing as e to the x plus e to the minus x over 2. So again, let's consider the e to the x function, which is this line, and the e to the minus x function, which is this line, and what happens when you add those two lines together and divide by 2. So hopefully you can see clearly that adding the red and the blue line together here is going to give the graph of cosh, which looks like this. Some things to note. This is not a one-to-one function. So therefore, in order for its inverse function to exist, we're going to have to restrict its domain to make it a one-to-one function. So in order for the inverse cosh function to exist, we will have to say that x has to be greater than or equal to 0 to make it a one-to-one function. Also note that cosh is always greater than or equal to 1. So its range is greater than or equal to 1. Our final bit of the video is we're going to look at the Tange function. What does that look like? A little bit more complicated to do this. So we've got e to the 2x minus 1 over e to the 2x plus 1. Let me draw a set of axes. And we're going to investigate what happens. Oops. Right, first of all, let's think about what happens at the origin. So when x equals 0, Tange is going to be e to the power 2 times 0 minus 1 over e to the power 2 times 0 plus 1, which is 1 minus 1 over 1 plus 1, which is 0. Excuse me. So it's going to go through the origin. It's going to go through 0, 0. Now let's consider other x values. First of all, let's consider the positive part of the graph. What happens over here? To do that, I'm going to say let's see what happens when x tends towards a really big positive number. So when it tends towards infinity. Now to help me to do this, I'm actually going to rewrite the Tange function because the way it's written at the moment, if I say e to the 2x minus 1 over e to the 2x plus 1, by me saying that x tends towards a big number, as it tends towards infinity, well, this is going to tend towards infinity, this is going to tend towards infinity. I'm not sure what that's going to become. I'm not sure what that graph's going to look like. But if I do a little trick, and I'm going to divide everything on the top here and everything on the bottom by e to the 2x. So e to the 2x divided by e to the 2x is 1. The 1 divided by e to the 2x is 1 over e to the 2x. On the denominator, the e to the 2x divided by e to the 2x is 1. And the 1 divided by e to the 2x is 1 over e to the 2x. Now, the reason I've done that is because now, in this limit as x tends towards infinity, this is going to tend towards 0. And this is going to tend towards 0. And so what I can see then is Tange is going to tend towards 1. So as x becomes bigger and bigger and bigger, Tange tends towards 1. We have an asymptote here at 1. So my graph is going to look like this. Now let's consider when x tends towards negative infinity at when x is negative values now. This is actually a little bit easier to do. I don't have to do any algebraic manipulation for this. Because when x becomes a really large negative number, I know this is going to tend towards 0, and this is going to tend towards 0. I know that without any algebraic manipulation, because let's remind ourselves what the e to the 2x graph looks like. Remember, it looks like this. And so as x tends towards negative infinity, my graph tends towards 0. So, if this tends towards 0 and this tends towards 0, then the whole thing is going to tend towards minus 1 over 1, which is minus 1. So we have a negative 1 asymptote down here as well. And my Tange graph is going to look like that. So there we have it. That is what the hyperbolic functions are. That's how they're defined. This is where they come from, the hyperbola, and this is why they're defined in the way they are with cosh and sinh, and how they're related to the trigonometric functions, because that's going to be a common theme when we're going to start looking at hyperbolic identities later on.